Okay, here we go again. Welcome back to some more online calculus. Starting to get a couple of views, so that's encouraging. Not sure if it's from you guys or some randos that are looking it up on the internet. But if it is you guys, keep up the good work. So what we're going to do today is we're going to do a little review of inverse functions. And then tomorrow we're going to use that to talk about how to find the derivative of an inverse function. Okay, so this should be pretty basic because this is something that you talked about for sure in Algebra 2 and also in pre-calculus last year. Blah, blah, blah. So inverse functions, quite simply, I'm sure you remember, are where you take and you switch the x and the y. So if this is a table of n as a function of t, if you switch the x's and the y's around, then you get a table of values which would be, t as a function of n. So there we go, rocket science. If you start with a function, and then you do the inverse of the function, and that is also a function, then you have a situation where you have something called a one-to-one function. I don't know how that happened. Huh. Oh, weird. If I click both, then the line expands in both directions equally. Huh. Interesting. I don't know why that would be useful, but always good to learn new tricks. Anyway, so if you are doing, if you have a function that's one-to-one, then both the original and the inverse are functions. So this is a function because you never put the same number in twice and get the same answer back. The inverse of this would also be a function because if you think of these as the inputs and these as the outputs, then again you never put the same thing in more than once and get a different answer back. This, however, to start with is a function because if you never put the same number in and get the different answer each time. But if you think about this as being switched around the other way, then the inverse is not a function because in this case if I plug in 4 I'm going to get 3 or I'm going to get 2. And since I don't know which one I'm going to get, that makes it not a function. So this is an example of a relation that's one-to-one, and this is a example of one that is not. So again, one-to-one is if both the, here it is, the function is called the one-to-one function if it never takes on the same values twice. And so since we're talking about inverses, the way that you find out if something is one-to-one is the inverse of the vertical line test. I'm sure you remember the vertical line test, which is if I take this vertical line and pass it along the graph and it never crosses more than once, then that is a function. The horizontal line test is how you tell if a function is one-to-one. If I take a horizontal line and run it along the graph, then you can see that that horizontal line crosses the graph more than once. So that means the inverse would not be a function, which would mean that the function is not one-to-one. So for a function to be one-to-one, in short, it's got to pass both the vertical line test and the horizontal line test. And if you think about it that way, then it's super easy, okay? And so the reason why they're not adding on the vertical line test to this definition is because they are assuming that it's a function already. So we're assuming it's already passed the vertical line test, and if it also passes the horizontal line test, the inverse is a function as well. All right, so is the function f of x equals x cubed a one-to-one function? Well, let's take a look at the graph, and then I bet you can figure it out. So this tool I was messing with earlier seems to sort of like smooth out, makes like line segments. I think if I was actually on the board, that'd be a good one to use. Anyway, oh, I drew it wrong anyway. Y equals x cubed. Looks like, oh, did I draw that wrong? No, I did that right. Yeah, two parabolas. Okay, so it looks like that. So since this passes the horizontal line test and it passes the vertical line test, that means that, whoops, yes, this functional is 1, 2, 1. Okay. How about if we consider the function y equals x squared? So that means we can look at the graph, and hopefully in the time that it takes me to draw the graph, you'll have answered the question in your head already. And that is that no, this is not one-to-one, because there's lots of different places where I could draw horizontal lines that would cross that graph more than once. Okay, so that's a general idea, real basic. Okay, little notation. If you're doing an inverse function, hopefully you remember, then you write it as with a little -1 exponent. But be careful to understand that the -1 in this is not an exponent. F to the -1 of x does not mean 1 over f of x. If you wanted to write the reciprocal, if you wanted to write 1 over f of x to not confuse the notation, you'd have to write it like that, okay? And so since in an inverse function you are switching the x and the y's, the domain of the inverse is the range of the original, and the range of the inverse is the domain of the original. Okay, so that is some super exciting stuff. So let's take a look at an example here. Let's say that we know that f of 1 is 5, f of 3 is 7, and f of 8 is -10. Then what is f inverse of 7? So that question is asking what value would you have to plug into the original function to get 7 as an answer. So since f of 3 is equal to 7, f inverse of 7 equals 3. What then would f inverse of 5 be? In other words, what value would I need to plug into the original function to get 5 as an answer? Well, f of 1 is 5, so that means f inverse of 5 is 1. And finally, if we wanted to figure out what f inverse of -10 is, again, we would be asking what value would we have to plug into the original function to get -10 as the answer. And you can see from this right here that that answer would be 8. Okay, this is a lot of, oh, no, this is relatively important, I guess. If you compose a function with its inverse, since they're each canceling out what the other one was doing originally, f inverse of f of x would be x, and f of f inverse would also be x, and that's because they're inverses, obviously, so they're undoing whatever the other one did. All right, so let's do a quick review of how to find the inverse of a function. 3 steps. 2 steps. Write the switch the x and the y's in the function, and then solve the equation for y. So let's do the super easiest one you could ever imagine doing. Let's start with y equals 2x, okay? So the way that you would find the inverse of that is to start with, you would switch the x and the y, and then you would solve this for y by dividing both sides by 2. So in this case, y would equal x divided by 2. And to indicate that this is the inverse that we have found, we would really like to go ahead and use that notation. So in this case, the inverse would be x divided by 2. Switch the x and the y, solve for y. All right, so let's try one that's a little bit more complicated. To find the inverse of the function f of x equals x cubed plus 2. So I'm going to start by rewriting this as x equals y cubed plus 2, and then I'm going to solve that for y. So first step in that process is to subtract 2. So x minus 2 equals y cubed. And then to get rid of this cubed, I have to cube root both sides. That means y equals, let's see, we need the cube root. So y equals the cube root of x minus 2. Okay. So that would be my inverse function. Switch the x and the y. Took me 2 steps to solve for y. Subtracted 2 and then cube rooted both sides. Okay. Okay, one more thing that's fun about inverse functions is that graphically, since you're switching the x and the y's, since you're taking this original point a comma b and then changing it to b comma a, you have, what that does to the graph is it essentially reflects the graph over the line y equals x. Okay, so that's how that looks visually. So the graph of the inverse is obtained by reflecting the graph of f about the line y equals x. Funsies. Okay, so let's do this last example, and then I'll give you some problems to work on if you want. Because again, this is just a review, so there's not that much for us to talk about. So the first thing I'm going to do before I try to make this graph is I'm going to see if I can rewrite this square root into a form that is at all understandable to me. Meaning, come on, oh, I gotta click on here. Meaning that what I'm going to do is I am going to take and factor out a -1 because I don't like having a negative x, and I'm also going to switch these guys around. So I'm going to make this x plus 1, like that. So you can see if I distributed the -1 there that I would end up with the same thing. -1 times x is -x, and -1 times 1 is -1. The reason why I wanted to do that is because now I might be able to do this just by using transformations of graphs. I know that the square root function looks like this. I know that the +1 is going to move that graph 1 to the left. And then I have this negative, which is essentially inside the parentheses because it's underneath the square root, which would flip that graph over the y-axis. And so I think that that means it's going to look like this instead. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so let me just check that with a couple of points real quick. If I plug in x equals 1, oh, no, that negative is screwing things up. So fail. If I plug in, I can't plug in x equals 1 because then I would get a negative underneath the square root. So I can only plug in values that will give me negative right here. So I'm going to start by plugging in -1. So nope, I can't do that either. Yes, I can. If I plug -1 in there, -1 plus 1 is 0. 0 times -1 is also 0. And so if I plug in -1, I get 0 as an answer. So that gives me a point right there. If I plug in -2, oh, okay, so I don't know why. Oh, it reflected. I see, okay. So I had it moved to the left correctly, and I had it reflected correctly. I just should have done the reflection first and then moved it to the left. Sorry. Anyway, so if I plug in -2, -2 plus 1 is -1. -1 times -1 is 1, and the square root of 1 is 1. So hopefully you can see the graph starting to take shape here a little bit. Let's see, 1, 2, 3, 4. So the next thing I'm going to do is plug in -5. -5 plus 1 is -4. -4 times -1 is 2. And I'm sorry, -1 times -4 is 4, and the square root of that is 2. So -1, 2, 3, 4, 5, and then 2 gives me that right there. Let me see if I can use my new Funkadelish tool. Try and draw better. I don't know, not so great. Whoops. Okay, so there's the original graph, f of x. Now I'm going to graph the inverse. And so that's really easy because I have done most of the work already. All I need to do is just flip the x and the y's on these points. So instead of being at -1, 0, I'm going to be at 0, -1. Instead of being -2, 1, I'm going to go to 1, -2, and now you can kind of see the graph taking shape, hopefully. And instead of being at -5, 2, I'm going to go to -5. And so this graph is going to look like that other one, but it's going in this downward direction instead. And these are both a reflection across the line y equals x, like that. Okay? Alright, so that's a quick review on inverses. Here are some problems for you to do if you would like to make sure you understand it. Go ahead and I know I haven't made a video the last couple of days of me going through the problems. I'm going to go ahead and do that today because there's some good ones in here, and having a basic understanding of how inverse functions works is muy importante for our work going forward. Alright, so hopefully you'll tune into that video momentarily. Bye-bye.